Okay, we are set now. So, uh, okay, so this is if you're given this curve, of course, as the line, let's call it y is equal to f of x. And then you're told find the region, find the volume. Okay, find the volume of the region bounded by that curve. And maybe they give us A here, and they give us B here. So it's bounded by that curve, the y, and also the x-axis. And then these two vertical lines, A and B. If the revolution is done about the x-axis. So, what do I find it? So here you have to calculate. So they ask you to calculate the volume of a generated solid of revolution by revolving two-plane region bounded by f of x bounded by f of x, the vertical lines x is equal to A and x is equal to B, rotated about the x-axis. So I'm giving a general case where they give you a curve, and then they are asking you to find the volume of a generated solid of revolution by revolving a plane or two planes, two-plane region bounded by that f of x given, and the vertical lines x is equal to A, x is equal to B. Of course, the base there because you are revolving about the x-axis, so you'd consider that x-axis as a boundary also. So when they ask you to do that, you know that as you revolve, so if it's about the x-axis, or this curve that is up there, same distance, you have another curve down here, same shape. And then you are saying, oh, so the revolution is done here. This is what you expect to have as a new curve, as your solid, this thing. So you know these are shapes that you have learned now, like you know what they are. So like it's growing, it's forming these as you do the revolution here. These are being formed like that. So it forms this kind of a shape, which is why we're saying the disc method, because it forms something like a disc. And then how do you find the volume if you are given such? That's our interest. So this was just so most times you don't even have to maybe get to the structure itself. You just look at what is given, information given, and then say, okay, so the volume of this is going to be the integral of the area with respect to x if it comes in this form as f of x, or well, if it comes as If it comes as f of y, then you're finding the integral of the area with respect to y. Because now you're understanding that in this case, this is with respect to y. Then this is with respect to x, like that. Now you understand that all these, when you say the area of a disk, it's just a simple thing as pi, and then you get the function. So if the function is y here, so you get y and have it squared with respect to x, like that. Or because now we know y is f of x, we can as well write this as pi and then f of x squared with respect to x. Of course, in this way, it has to run from a to b. It has to run from a to b. If it was the other side, you would say pi x squared dy, because we are saying from a to b, we're now saying this is pi, and then this is f of y, and then squared and dy. That's why we are putting x dy. Not that we have two variables, but because we understand that x is a function with respect to the y variable. And so this is one of the nice questions that you ask you, and they mean that you always have to come up with a sketch. But if you write sketches, you can see what is going on. You try to sketch and then do the integration there. A nice example. A nice example here, following this, the application of the disk method, and then how you know that this is now the disk method. How do you tell when a question is asked? So the example must help us tell that, oh, this is the now a disk method. Okay, there's a hand raised.
Yeah, so do we consider the volume from the Z positive part, or it's all the way?
So what would happen if you had to drive this? You'd understand that when you say area, it's using the radius. So because of the issue of the radius, when you have these like that, and then you do this, well, it doesn't really necessarily that mean that we are cutting this in between. Now. We are getting the volume of this whole thing, but we'll be using this radius. When you say radius, it means that even this part will be presented. It's like you're dealing with a circle, right? And then you pick the radius. It doesn't mean that this other part has been thrown out. No, we've included it, but we've just used its right part. It's halfway information. So we're not separating the volumes, we're getting the whole thing.
Okay.
Yeah. Okay, let's do an example. Example. Determine the volume of the solid generated by rotating the region bounded by f of x is equal to x squared minus 4x plus 5, x is equal to 1, x is equal to 4, and the x-axis, okay, about the x-axis. So we are saying determine the volume of the solid generated by rotating the region bounded by f of x, x is equal to 1, x is equal to 4, and the x-axis. And the rotation is happening about the x-axis. So if you want, as you answer this, you may attempt to sketch. So in this case, just make a rough sketch. So that is if you understand the sketches. So this is y, and this is x. So what are we sketching? The function itself. And so we're just interested in sketching it from 1 to 4. So you pick one, substitute in the function. What is f of 1? F of 1 is going to be 1 squared minus 4 plus 5. This is like 6 minus 4, which is 2. So we have 1, 2 somewhere there. And then pick 4. What is f of 4? F of 4 is 4 squared, which is 16, minus 16 plus 5, giving us 5. That is 4, 5, somewhere there. But then you know this is a quadratic, okay? If you want, you can get an idea of its turning point. That's normally what you do if you have a quadratic. At least you must know the turning point, or just an idea of what the turning point is. So, which we get as x is equal to negative b over 2a. That is negative 4 over 2. So we get 2. So it means that it's somewhere here at 2. So we substitute 2 back there. We have 4 minus 8 plus 5. This is 9 minus 8, which is 1. So it's 1 somewhere here. So meaning that this is a curve. Because we are attempting to sketch. So you know it has a turning point there and go up like this. So we haven't sketched it scale, but this is the idea of the sketch. And so we're talking about the evolution about these lines. So we know that, well, it has to go down there a bit and then also come from there. Of course, of the same magnitude going down. So it means I'm saying here, I would need a 2 as well. And then I would need the negative 5. So that as I do this, at least I'm aiming at getting there, and I'm aiming at getting here. And down here, I should have, of course, a negative 1. So that somewhere there, this guy is going to go as well, turn and come down like that. So I'm talking of this region here. I'm talking of which region? I'm talking of this solid here. This solid space. Like this solid space. And so what's key? Also, we're doing this so that you can just get an idea of what the revolution is going to be about and how does it look like? What's our interest? So of course, you know, you have got these lines from these spaces here. You have got these that can be formed here. You've got this. So these can be so many of them. because it forms a solid thing. Like that. So we're doing this because it's about the x. So if it was about the y, you would have done that about the y. So we would always push it to the y and then do that. Okay. Then what next? So next, we now want to get the actual volume. So you say, okay, the volume of this is integrating from 1 to 4 because we are given the vertical lines 1 and 4 from 1 to 4, and then pi, then by f of x squared. So f of x squared, and then with respect to x. So this is going to be 1 to 4. If I can put pi outside, what is f of x? F of x is x squared minus 4x plus 5. That's to be squared, and then dx. So we can simply do this squaring here. This is pi 1 to 4, and then this is going to be x to the power 4. I'll do square. So I'm multiplying x squared minus 4x plus 5 by itself. Right. You can do that, I know. So this is what you're going to get. X3. For us, we are doing binomial in the first is it's now an easy thing to do that. Just use my binomial skills, I have it. Hope you guys haven't forgotten the binomial skills. If you did, then you're in for it. Then now we start integrating. So the pi is still outside, and then integrate. That becomes x5 over 5. We're just using the standard power rule here. And 8x4 over 4 plus 26 x3 over 3, and then minus 40 x squared over 2 plus 25x. You want to substitute from 1 to 4. And to substitute, I just simplify inside. So we get pi, and then 4 to the power 5, 5 over 5, minus 4 into 8, that is 2, and then 4 power 4, minus 26 over 3, and then 4 power 3, minus 20 when you do 2 into 40, and then 4 squared is 16, plus 25 by 4, that is 100. Minus, we are now substituting 1, so we have 1 over 5. That one becomes plus 2, and then minus 26 over 3, and then plus 20, and then minus 25. So you simplify this one now. What do we get? So we should be able to get 78 over 5 pi. Like that. So because these are, this is volume, so we write units cubed. So just look at how the function is given. If it's given in terms of x, yes, whatever function, this thing that will be called f of x is what you square here. So you could do this even without having to sketch. What do you mean the square? How do you square this? How do you multiply this? ordinary way. Say x4. And then when I go to the power 3s, I'll say x squared times 4x. Okay, good. Okay. So we also have this same disk. Now it will be named the washer method. And what makes it to be called washer method? So the second case, I want to talk about the washer method. Well, so if in your notes they're not mentioned, but they're there, obviously for you to do this interpretation around the revolution, you have these methods. Maybe they may not be mentioned, but they should be mentioned in any one. So the washer is the extension of a disk method. Okay. Where now for the washer, you have two functions. You have two, instead of having one function, like in this case for the disk, we had one function, f of x. Now for the washer, we'll have two functions, f of x and maybe g of x. And then we'll still have x is equal to 1, x is equal to 4. So we'll still have those lines. So once if I have one function and two lines, I'm using the disk method. If you just check what lines are given here, the ones that you're going to use. Then if I have two functions, f of x, g of x, then I'm also given x, then I know it's now the washer method. Just for the sake of differentiating, like knowing, oh, which one am I using now? So if I'm using the washer, you expect to have, you're looking to find, what should be the question? To find the volume of a solid generated by a region between f of x and g of x bounded by the vertical lines x is equal to a and x is equal to b, which is revolved about the x-axis. Yeah, like that. So the volume here is going to be given by the integral from a to b of pi, and then f of x squared minus g of x squared dx. So the reason why we're putting this absolute value is to allow you to have that flexibility. Well, you don't really need to check which function is lower than the other. You know, even if I have a curve like this, and then I'm given this function against this function, and I'm given these lines. I don't need to be bothered that this function is higher than the down function. So it will be this one. This is f, this is g. So it has to be f minus g. Well, I can even do g minus f. For as long as I remember that when I find my answer, if it is positive, I'll put in the absolute because I know that it was supposed to initially be positive. That's what the absolute mean there. They don't mean much. That's the question.
So the absolute value also applies to the area.
Yes, it also applies to the area.
Okay.
But if you look at the area mostly, we don't put it. Maybe it's because we want to force you to know which function is that and the other, because the area mostly will ask you to sketch it. So that you're able to see what is happening. That's why the absolute are hidden, so that you're able to see which function is on top of the other. Like that. So if it is brought in terms of, so this was where x is a variable. This was where x is a variable. Okay. But well, you could do the same thing. You could do the same thing with y now. You'd say maybe c to g, and then pi here, and then f of y squared minus g of y squared dy. So this happens when y is a variable. So we are talking of x be equal to f of y. Here we are talking of y f of x and y g of x. So here x g of y. So really, how you know that it's now this method? Once I'm given functions, two functions, and I've loved it, so I'll just get those two functions and square them as I subtract them inside. And you call it the Washa method. Seems like they were named nicely. Okay, so maybe we also need to talk about the one that hangs in the space. If they tell you that you're doing the revolution now, not about the x-axis, you're doing maybe the revolution about the line x is equal to maybe 2, where you are away from the x-axis. Instead of doing it on the x-axis, I mean, this was y is equal to 0. So instead of doing it on the y is equal to 0, maybe you do it on y is equal to 2. So where your revolution is done somewhere here, the function was there. So you want to know what happens. So when it was the x is equal to 0, you know 0 does not do much. But now you imagine if this was, if that is 3, then you need to go a bit down. If that is 3 and then this is 1, so you have 2. So the other one should be at -1 as you draw it down. So you need to know how we are taking care of this now. This region that is whose radius now has been stretched. It's no longer the actual initial length given in the question, but it's a bit tempered with, it moves a bit. So I think that would be nice from the sheet and direct. So I just thought of introducing this. Today, I'm not aiming to go very far. At least I'm able to come back and have a class. So that Daniel and Moses don't go again. Because I'm now
Some of us are depending on you.
yeah, now to the exam. So the Benwick, Mike. And is up.
So, sir, timetable are we going to be following?
When is the Benwick fest? When are you writing a test for this course?
Monday.
Writing on is it the 10th? Mathematics should no, to be on 12. Mathematics.
Next week. Monday, yeah.
Yes.
What's the coverage?
The coverage. Guy, what's the coverage?
More likely from application of integration to series.
So sheet 6 to tell sheet 1. 7 or 8.
Yes, should be 7 or 8.
Okay. So on the applications, I think, so because of the Monday thing, so I think I'll meet you on, I should meet you tomorrow. Then I should meet you on Wednesday. I should meet you on Thursday. Yeah, then we'll be done.
Yeah, so it's very serious.
Yeah, you'll be
Mr.
able to-
Chisha is cruising.
So tomorrow we'll start a bit late because I have a class ending at 20. So maybe tomorrow we'll start at 21. But Wednesday we'll start at the normal time. And maybe we'll just lengthen it a bit. Maybe we'll go up to 20, 21, 30. So make it like 2 hours. Thursday the same hour, the class ending at 20. So we'll start a bit late. That's 1. And then stretch it well in. So it should be at least tomorrow we should finish the terror sheet for integration application. Then Wednesday another one, Thursday. They're not difficult things. It's just a summary of them. So that's how we proceed. No problem. Okay, we end here today. It was just an intro. Quick.
Sir, before we go, is it possible, like after maybe the class be sharing the notes, like
Yeah.
what we are solving?
Yeah,
PDF form?
starting tomorrow.
All right, thank you, sir.
Okay.
Even the videos for the recording, sir.
Okay.